Now, let's talk about infinities. This is actually a very interesting topic in theory of computation. Infinities, you know the notation of infinities. You write infinities, like this. So now, infinity means, boundless or endless. For example, normally when you write infinities, you give it like this. Okay, 3 dots, you say it is infinity. For example, you can say the set of real numbers, it is infinite. Hope you know what is a real number. Real number is something which comes you have a number 1.8123. That is a real number. And then you have set of natural numbers. Let's say 1, 2, 3, etc., etc., etc. Okay, so we know that real numbers are infinite. We even know that natural numbers are infinite. Now, people at a point of time, they started telling that, infinities itself, there is a difference in the type of infinities. Or in other words, I can say some infinities, they are bigger than the other infinities. Some infinities, they are bigger than the other infinities. Actually, this line, some infinities are bigger than other infinities, it is actually taken from a novel. Those who have read this novel, The Fault in Our Stars by John Green. This is a very interesting novel. Those who haven't read it, you can read the novel. It actually talks about a cancer patient, a 16-year-old, a cancer patient girl who tries to overcome her disease, and then she falls in love with another patient who was an amputee who lost his leg and all that. A very interesting story by John Green. It has even come out as a film, The Fault in Our Stars, an English film, a very nice, sweet film. Those who are interested in Hindi films, you might have happened to a film called Dil Bechara. Yeah, Dil Bechara. Dil Bechara is the Hindi adaptation of The Fault in Our Stars, Hindi adaptation of this novel. I think it was Sushant Singh Rajput's last movie before he passed away, 2020. Though it didn't have a theatrical release, I think it was released on the platforms, OTT platforms. Anyway, in this particular novel, The Fault in Our Stars, they talk about this. Some infinities are bigger than other infinities. Okay, so you have two infinities. I'm talking about the set of real numbers and the natural numbers. So when you say this infinite is always not always infinite. I can say that some infinities, they are greater than the other infinities. So let's think about a possible mapping. Okay, so let's try to prove that some infinities, they are greater than other infinities. So I'm trying to do a mapping between chairs and students. I do have many students and I do have many chairs. Okay, you can even think the other way around. I just wrote a chair and students. So I have chair number 0, 1, 2, 3, 4, 5, 6. It goes on and on, infinite number of chairs I have. And I imagine this chair to be a natural number. So I've written over here, chair, I'm doing a mapping between N and R. Imagine this chair to be a natural number and the student to be a real number. So I'm mapping chairs to a student. So what I have in mind is each student, I'm giving a chair. Each chair is for a particular student, and that student will sit on that particular chair. Now I'm just doing the mapping between 0 and 1. So I have a student called point, or it need not be 0 to 1. You can take any numbers, let's say 1 to 2 or whatever. So if I give from 1 to 2, instead of the 0, I will have a 1 over here. That's it. Anyway, for simplicity, I'm taking from 0 to 1. So I do have a student called 0.5239, etc., etc. And that student, he will be given chair number 0. So that student, he will happily sit on chair number 0. And now I have a next student. Now, the next student is 524. This is the random number. What I've done over here is I've just changed a small number. Okay, all the other numbers are different, but I've just changed one position. This 3, I have made a 4. Okay, so I take any position and then I make a small change and all the other numbers remain the same, still I can say that it is a different number. It is a completely different number. So when I've made a small change in a number, I can no longer give 0 chair to the second number. Okay, I can no longer give this because this chair is already given to this particular student. The number is almost the same except for a small change. But even though I have that small change, it is a different number. I call it to be a different number, which means I cannot give chair number 0 to the student. I can give another chair. So let's say I'm giving chair number 1 to the next student. Similarly, I do have n number of students. I do have n number of chairs, and because all of them are different, I allot chair to this student, the 1th chair to this student, the 2th to this, the 3th to this, 4th, 5, and then I go on, and then I assign chairs to all my students. Okay, now look here. What I'm trying to prove is, I am trying to prove that, see, this is my natural number and these are my real numbers. So what I am trying to prove is both are infinity, natural numbers are infinity, R is also infinity. But what I'm planning to prove is the infinity of R is a bigger infinity than N. The infinity of R is a bigger infinity than N, and R, in other terms, I can say R is uncountable. I'm trying to prove that R is uncountable, which means as R is going to be a bigger infinity, there will be students who do not get chairs. Okay, there are infinity chairs, there are infinity students, but because R is a bigger infinity, there will be students who do not get chairs. Or I can say in other words, there is always going to be, I went wrong way. There is always going to be a real number which cannot be mapped onto a natural number. I went wrong over here. Now, this has been proved by an argument called the diagonalization argument. Okay, so the diagonalization argument, what it proves is, it proves that R is uncountable and the infinity of R is greater than the infinity of N. So let's see how it was done. Now, there was this mathematician and philosopher called George Cantor. Even though we say it, we pronounce it as George Cantor, it is actually Georg Cantor. Anyway, Georg Cantor, he came out with the Cantors Diagonalization argument. It is even called Cantors Diagonalization slash, SLASH. Cantors Diagonalization slash. This George Cantor, he's actually the creator of the set theory. He was a very great mathematician of his times. And then in his biography, it is being told that he was too much into mathematics that, whenever anybody started to prove that any of his mathematical statements were false, he actually went into a depression. Okay, we did see that there were things like comprehension principle, naive set theory and all, which did have its own flaws. And Georg Cantor, he took many of these things very personally, and then he went into depression. And during the end of his life, he was always into these mental hospitals, sanatoriums. That is how he passed away. He was into mental depression for a very long period of time. So anyway, Georg Cantor, he came up with something called Cantor's Infinities. Cantor's Infinities, where he tried to prove that R is uncountable. So let's see how this great mathematician did it. Okay, now, as you all know, we have all these, we have a chair, we have a student, and then, we do have all these numbers. Now, in the diagonalization argument, what Georg Cantor did is he took diagonals. he took the diagonal of the number. Okay, so when I take the diagonal after the decimal point, I've selected the first number over here, I've selected the second number over here, the third number over here, the fourth number over here, the fifth number over here, and then I've selected the sixth number. So this is how he started off with his diagonalization argument. For all the real numbers, he took the diagonal part. Okay, and then what he did is he just added up a random number. He took a random number, let's say 1. He took a random number 1, and then he added that same number to all these elements. Okay, so imagine I took 1, I did a 5 plus 1, I got a 6. 2 plus 1, I got a 3. 3 plus 1, I got a 4. 9 plus 1 is a 10, which I got a 0. 0 plus 1, I got a 1. And 5 plus 1, I got a 6. Okay, so he took the diagonals and then he simply tried to add up a number, a random number. For this example, I just took a number called 1, and then he got a new number. This is my new number, or I say I got a new student. I got a new student, 0.634016. Now look here. Now there is only a slight change between 5 and 6 over here. Look here, the first position. I'm talking only about the first position. There is only a slight change, 5, and this is 6, a slight change of 1, but still it is a different number. But anyway, we know that for this particular student, I cannot give chair number 1. I cannot give chair number 0, because chair number 0 is already given to this particular student. Chair number 0 is already given to this particular student. Now take the next position, 3. There is just a slight change between this 2 and this 3, a change of 1, but there is a change. There is a change. And you cannot think of giving chair number 1 to this student, because why? Chair 1 is already given to this particular student. Now the same way, think 4, 3, a slight change, but still it is a change. It is a change. Can you think of giving chair number 2 to this 0.63 student? No, because it is already given to this student. And then you think about each and every chair. You think about each and every chair. You cannot give the chair to this student because you already have a student who's sitting on that chair. So very simple. I do have a new student over here who does not have a chair. So, the new student whom I now created, he is simply standing. He doesn't have a chair. I'm creating another student. I am creating another student. Now, for the other student, what I'm doing is I'm taking the same diagonal. I'm taking the same diagonal. Instead of adding plus 1, I am adding plus 2. So 5 plus 2, 7, 2 plus 2, 4, 3 plus 2, 5, 9 plus 2, 9 plus 2 is 11. 9 plus 2 is 11. Okay, so this is a 1, I'm sorry. And then 0 plus 2, 5 plus 2, 7. Okay, which means, I am getting a new student. Now, I'll use the same logic. Take the 0th student. Okay, there is only a small difference between 5 and 7. It is still a difference. Think whether you can allocate chair number 0 to your new student. Think whether you can allocate chair 0 to your new student. You cannot give chair number 0 to your new student because it is already taken by this particular student. Now go for the next 4. 2, 4, a difference of 2. Let's think. Can you give chair number 1 to the student? You cannot give because this student already takes that. You go check each and every number. Anyway, you cannot give any chair to that student, which means that new student also you cannot give a new chair. So at the end of the day, you can create n number of new students, but all the new students which you create, they will not be having chairs, which means the number of students are more than the number of chairs. Or in very simple terms, I tell real numbers are more than natural numbers. Or in other words, real number infinity is greater than the natural number infinity. Very simple, real numbers are uncountable. So that is why they came up with something telling that natural numbers, you call them to be a countable infinity, and real numbers, they are an uncountable infinity. Okay, thus real numbers are uncountable. So that is why people say some infinities, they are bigger than other infinities. All infinities are not the same. Very simple. Real number infinities are greater than natural number infinity. Now let's see how George Cantor, he tried to prove it mathematically. He tried to prove it mathematically. So, very simple. He had a set of natural numbers and he had a set of real numbers. And then just like, I thought of a chair student, he thought about something called a function. Okay, so this is f0 of n, f1 of n, f2 of n, and so on. Okay, and now look here. When I think about f0 of n, I will be having a number in the 0th position. I will have a number in the 1th position. I will have a number in the 2th position, 3th position. When I look into my first number, there also I'll have something in my 0th position, 1th position, 2th position, 3th position, and so on. So, you think about any function, the first one will be the ordinal position, the position number of the number. Okay, and then the second one is the function. So here I've just written a very simple function. Here I've written a function like 2x. Okay, you can think about it as a function called f of xy. Okay, think of it as a function called f of xy. Okay, so my function is 2x. Okay, 0 into 2 is 0, 1 into 2 is 2, 2 into 2 is 4, 3 into 2 is 6, and so on. I just wrote a random function called 2x. Now here, the next function which I wrote is, okay, x itself. Okay, whatever is my x, my y is also that. Okay, so this is y is equal to 2x. This is y is equal to x itself. Okay, so whatever is my x, that is my y, 1, 1, 2, 2, and 3, 3, and so on. Here, what I did is I simply gave an x square. I just gave random functions over here, 0, 1, 4, 9, etc. Here, what I did is I gave an x cube. Okay, here I gave simply a 5x. I give random numbers. Here I gave a 5x. Here I gave a 10x, and so on. So on. Okay, so here actually my number will be something like this. Okay, if I think of my number, I'll write it 0 point. In my 0th position, I will have 0. In my first position, I will have 2. In my second position, I will have 4. And in my third position, I will have 6. Okay, let's come for my next function. I'll have a 0 over here, 0.0, 1, 2, 3. Okay, similarly, my next number, I'll write 0.0, 0.0149, and so on. So this is how I get my decimal points. I just gave a random function so that, these things are generated with respect to the appearance of the number. So let's see how Cantor tried to give a proof of this. Again, just as before, he took the diagonal. Okay, so 0th position, he simply added up a 1. He simply added up a 1 to everything. So in my 0th position, I do have 0 plus 1, which is 1. In my 1th position, I do have 1 plus 1, which is a 2. In my 2th position, I have 4 plus 1, which is a 5. In my 3rd position, I have 27 plus 1, which is a 28. So this is how he tried to get a new function called f dash of n. Okay, now what he tried to do is he tried to assign this particular function to a number. Okay, now look here, f0 is assigned to a natural number called 0. This is to 1, this is to 2, this is to 3, this is to 4, and this is to 5. Now what he's planning to do is he's planning to assign this f dash to a particular number. Now let's see how he tried to do this. Okay, now look here. He first took this number and then he checked whether it can be assigned to the number called 0. Just like earlier, there is only a slight difference of 1, 0, and 1. So it checked whether this can be assigned, this number can be assigned to the new f dash. But he cannot assign it because it has already been assigned to this particular function. The same way he took the second part. He took the second digit. He took the next number 2. There's just a slight difference between 1 and 2. He's thinking whether he can assign this one number to this new function f dash n. He cannot because it is already assigned to f of 1, f1. The next number 2, 4, 2, 5, only a slight difference of 5. So let's see whether we can assign the number called 2 to f1n. You cannot because it is already given to f2. Take the next number, just a slight difference. Check whether you can assign f dash to number 3. You cannot because it is already assigned to f3. So look on top, I've written over here. F dash can't be assigned to f0. F dash cannot be assigned to f1. F dash cannot be given to f2. F dash cannot be given to f3. You go on checking and checking. You cannot find an allocation for your new function called f dash. Now imagine you take up another number, f double dash n. F double dash n, you take the same diagonal argument. You take the same diagonal argument. Instead of adding up 1, add up any other random number, let's say 2 or 3 or whatever. You apply the same logic. You will not find an allocation for the new number called f dash n. So that is why Cantor told the new functions which you make, the new functions f dash, f double dash, f triple dash, f any number of dashes, they do not align to any natural number called n, which means it comes under the category called uncountable infinities. Thus, R is uncountable.